Good morning, professors, and welcome to this enlightening experience with the Science Bus. Today, we shall explore how to determine the relationship between the period of oscillation of a pendulum and the length of the string. This educational experience is especially appropriate for high school students, and we will require the utilization of the mechanics kit. To efficiently conduct this experiment, we must begin by firmly securing the vertical rod into the support base. Let's proceed by taking a clamp and carefully inserting the shorter rod into its designated housing. Subsequently, we will securely fasten the clamp to the vertical rod. Now let's select a mass, specifically one that weighs 50 grams, along with some string. We carefully cut a segment of the string and fashion two loops, securing them with two tight knots, one encircling the support rod. Into the other loop, we will insert the mass. Let's take the protractor and carefully adjust the pendulum to an angle that is less than 15 degrees. Allow it to swing freely. At this juncture, using the stopwatch, we will calculate the duration taken by the pendulum to complete a total of 10 full oscillations. We are consequently able to accurately determine its period and frequency. The period of oscillation of a pendulum is precisely defined as the duration it requires to complete a single full oscillation, which is the time it takes for the pendulum to return to its original point of maximum extension. The frequency of oscillation, on the other hand, is the number of oscillations the pendulum completes in 1 second. The frequency is determined by calculating the reciprocal of the period. At this particular juncture, we have the capability to compare the two different outcomes of the period, the one computed by utilizing the stopwatch and the one derived by measuring the length of the string with the meter. Let's trim another section of the string, ensuring it is shorter than the previous segment. We will create two loops at the ends. In one loop, we will place the mass, which remains at 50 grams, identical to the previous mass, and the other portion of the string will be securely anchored to the support rod. Once the system is liberated to move freely, we will observe two distinct frequencies, even though the mass remains unchanged. This is due to the fact that the period of oscillation is reliant on the length of the wire and not on the mass itself. Specifically, observe how a reduced wire length corresponds to an increased frequency. Let's continue the experiment by taking a dynamometer, making sure it is set to 0, and now attach a different mass. We verify this by looking at the weight force on the dynamometer. Let's move forward by carefully taking the string. And now we must be quite precise, since we need to cut a segment of the string that is equal in length to the one that is supporting the mass. We should consequently achieve the subsequent configuration. As we have done previously, let's employ the protractor or any stable surface as a reference point to ensure the masses remain aligned and release them simultaneously. As we have observed, the oscillation period remains consistent for both of the masses. Professors, thank you for watching. See you at the next experiment.